Okay, assalamu alaikum wa rahmatullah. I think we stopped here last time, is it? Everyone, can you hear me? Okay. So we've looked at the transform impedances, sorry, and we know that for the resistor, inductor, and capacitor, it is R Ls and 1 over C times S respectively, as shown here. Oh, where is it? As shown in that in the slide. So for a series circuit where you have a voltage source in series with your L, C, and R, then we can write easily as the impedance is sum of the individual impedances. Right, so this is it. Now for the parallel circuit, we know that the impedance is the inverse, or the 1 over ZT is 1 over ZR plus 1 over ZL, 1 over ZC, which you can write in this form. And then we can simplify as much as we want. So now let's look at this now. Now, if you look at this, we have L2 and R2 in series, L2 and R1 in series. So we'll just have, for the first branch, we'll have R2 plus SL2, and then R1 plus SL. Okay, maybe let's assume this is 1. Let's assume, or if it is 2, well, they can be 2, both of them. So let's say SL2. So now, if they are in parallel, then we can just write R2 SL2. Remember in your circuit theory, right? So some things I will not go into detail because I know you did circuit theory, S201. So this one is R1, one is over the sum of them. So this will be R1 plus R2 plus S into L2 plus L2. So we can say 2L2. Assume if everything is L2. Or if it is L1, it will be L1 plus L2. So this is easy. Okay. Again, let's look at this one. You see, this is a parallel branch. So 1 over Z is 1 over ZR plus 1 over ZL, which is this. Or we can write it directly, R times LS over R plus LS. And then we replace that with this Z, which is in series with C. So once we do that, we know that we can apply Kirchhoff's current law. But now we are working in the Laplace domain, if you look. So it will be IS times Z plus 1 over SC times I is equal to VI. And then VO, the output voltage, which is the voltage across the capacitor, is going to be the drop here, which is 1 over SC times I. So if we substitute SC times V naught into the equation, why are we substituting that? Remember, we are looking for transfer function, and the transfer function is going to be V out over in. right? So if you look at this equation, we don't have V out anywhere, but we have IS here and we have IS here. So we can substitute for IS so that we will have V out coming into this equation. So once we do that, we have something like this, and then this becomes our transfer function. Is it okay? Okay, operational amplifiers. We know these equations for operational amplifiers. For the inverting amplifier, we know that the V out over V in is minus Z2 over Z1. While for the inverting amplifier, this is it, 1 over Z2 plus Z1. Is it okay? This example, I think we've done this example before. Yeah, we've done this example. Okay, I repeated a few slides then. Okay, so another example for the operational amplifier, right? So we know that V out over V in is minus Z2 over Z1. And this is Z1, which is R1. This is Z2. Z2, which is 1 over R2 plus 1 over SC, or it will be SC R2 over SC plus R2. So we can just substitute this value to the original equation. And finally, we would have this answer, right? We substitute Z1 to be R1 here, and then Z2 is this. So it's just this over R1. So straightforward. Once you remember this equation, you find your Z1 and Z2, and then you substitute. Okay? What do you think about this one? It looks very complex. Is it easy? So how do we approach something like this? To do something like this, we first of all find the ratio of V1 over V in. And then we find V out over V1. So, and then from this equation, we write V1 in terms of V in and substitute it here. So we find, so once you break it down into two circuits, find this, and then substitute, it becomes easy. Again, this is part of what you did in circuit theory. Let me see. Okay, so let's see. So let's start. So we know that this is an inverting amplifier. So we know that V1 over V in is equal to minus Z2 over Z1. Now for this system, what is Z2? Z2 is the impedance of this parallel circuit. So it is R2 times 1 over SC over R2 plus 1 over SC. So we have minus Z2 is R2 over SC over R2 plus 1 by SC. Then we divide this by Z1. Z1 is R1, so times 1 over R1. So if we like, we can multiply up and down by SC, so that we'll have 1 over minus R2 over, who drew line for me, over SC R2 plus 1 into R1. So we found this first part as V in over, sorry, V1 over V in is equal to minus R2 over R1 into 1 plus SCR2. Well, I will have to write, I may have to write it again because this is going to be wiped away. And then I can use the other part. Let me use this side. Let me use this side. We need to find now V1 over, sorry, V out over V1. So again, this is minus I over R in. So V out is equal to minus RF over R in times V1. Now from this equation, we find our V1. V1 is just this thing times V in. So we just substitute directly here so that our V out is minus RF over R in times V1, which is minus, so this becomes plus R2 over R1, 1 plus SR2 times V in. Or we can just divide this and just write V out over V in. I should have used whiteboard. Sorry, this space is not good. Is it okay? Following? Okay, good. Now, if you look at this, this is similar. The only difference is, if you look, the only difference here is this one is just R1, while here it is going to be R1 and C1. So all the other steps are the same. So maybe I will allow you to solve this as an exercise. Is that okay? Hello, everyone. Hello. Have you been hearing me? My microphone has been mute. I didn't know it has been on mute for a long time, and then I've been talking to myself. Raba, Ali, Makbal. But before you were not hearing me. So I was talking to myself for a long time. So you didn't hear what I said for this one. What I said here, so when you stop hearing me, okay, so when did you stop hearing? What I said is for this one, it is similar with this, the previous one. It's only that this R1 is now replaced with R1 and C1. And for the second one, is the same thing in the next one, only that instead of C1, R1, we have values here. So I said you can solve this one as, I will allow you to solve this one as an exercise, example 5 and example 6. Is that okay? I feel people are not. Where is everyone? You go somewhere? Okay, so let's look at mathematical modeling of mechanical circuits. So, if you remember from your mechanics, usually mechanical systems could be translational, would give linear motion, or rotational, giving us rotational motion. So we'll start with translational mechanical systems. In these systems, the main things are going to be mass, spring, and damper. So the basic elements, we'll start with the first, which is the mass. Now for a mass, if a force F is applied, then the force of mass Fm is, we know this, Newton's law is mass times acceleration. Now we know acceleration is, yeah, dv dt, the rate of change of velocity with time, which is d squared x by dt squared. That's the second derivative of position. So we can always write it as f is equal to m d squared x by dt squared, or we can write it as m x dot dot. Now remember, in Laplace, this is going to be, assuming zero in the initial conditions, m, if we take the Laplace transform of that, it is s squared times x of s, right? So we can always draw that in this way. This is the free body diagram from us. The next is the spring, right? So the force applied to the spring is proportional to the change in length. What is this one called? What is the law called? I think, is it Stokes? No, I'm not. What's the name? Well, the law that says F equals to kx. The force for the spring is proportional to the extension of the spring, right? So if k is the stiffness and we have position x2 and x1, if x2 is 0, then this is fixed. If this is fixed, x2 cannot move, is 0. If not, if both ends of the spring can move, then it will be x1 minus x2 is the deformation. So this x1 minus x2 will give you how long the spring is, and your F becomes here, in that case, equals to K, Hooke's law, yeah, Hooke's law, K into x1 minus x2. Thank you very much. I was trying to remember Hooke. Next is the damper. Damper is like a friction, right? So it opposes motion. We can represent it in this way. And then it is the force is the damping coefficient or stiffness times the velocity, which is x dot. So F is c into x1 dot minus x2 dot. And if this position is fixed, is not moving, then x2 will be 0 because it's not moving. So it will be F is equal to c times x dot. So we've seen three equations. Force is mass times acceleration. Force is, okay, you want to repeat the spring. Okay, I will go back to the spring. Okay, so if K is the spring constants, or this, the stiffness of the spring, we know from Hooke's law that F is K times X. Now, in some situations, you will have the spring such that both ends can move, x2 and x1. Then we know the extension is going to be x1 minus x2. So this is that case. But if x2 is 0, then it is only x1. So here it is k x1. Or here it will now be k into x1 minus x2. Remember, x is just displacement. Is it okay? Okay. Now consider this example. A horizontal spring mass system on a frictionless surface, so the friction is 0. Then we want to find the transfer function, right? So the force is the summation of two forces, right? The force due to the spring and the Newton's force due to the movement along x. So that is it. Mass times acceleration plus k times x, or mx double dot is equal to minus kx. So this is a model for that. Again, let's look at this one. So this one has, you need to look first. So you see, we have the force due to the spring, we have an applied force, and then this is the direction of motion. So we assume the spring is pulling this block this way, and then there is that force due to the mass, Newton's force, also this way, and then the applied force, you see we are pushing it this way, is going this way. So we know that F m is equal to Fk plus F, so this is F capital M, is Fk plus F small m. Sorry, that was a mistake. I wanted to say capital F is equal to Fk plus Fm. We know what Fk is. It is k times x, right? Hooke's law. Fm is Newton's law. Mx double dot. That is F. Right? So this is it. Mx double dot. So this is just the model equation. To find the transfer function, we take the Laplace transform, second order Laplace, we take the Laplace transform. The Laplace transform of f is f of s. Now this is m, because it is x double dot, assuming zero initial conditions, it's going to be s squared times xs. Again here, it is k times xs. So the transfer function becomes this, 1 over ms squared plus k. Is it okay? So we'll just say, remember always, when you look at it, what is your output? What is input? So the input is the force we apply to this, and the output is the movement. Let me go back. So remember, we apply this force, and the block moves by x. So this is the input, and this is the output. And transfer function is going to be output over input. So that is how to know what you are looking for. Right? Output over input. Is it okay? Okay, this is another system. So we added one more term now. Before we just had the spring and the applied force. And so here now we have a damper also. So it is also dampening. So we have three of them acting now. The spring force, the Newton's force, the damping force is equal to the total force. Right? Our output is x. Our input is this F. So we can write the equation as we wrote it before. Right? After writing the equation, we know this is Newton's law, this is the damping force, C times dot, this is the Hooke's law, spring force. And then we can take Laplace transforms of each side, both sides, assuming again zero initial conditions. So this is ms squared xs, cs xs, k xs. And then the transfer function is the ratio of the output by the input. If you notice, xs is common here. And then we have ms squared plus cs plus k, which is this. Is this okay? Straightforward? Where is everybody? Where are the others? Is only two of you around? Where is Abdul Hadi? Where is Ali? Where is Makbal? That means they are not online. Hmm? Where is Abdul Hadi? So some people just log in and then they leave and go to continue their activities. So if you look at this example, it is similar to the one we just solved. Now, again, we have the spring force, damping force. So K1 times F plus the force spring 2, equivalent K times equivalent constant. No voice. Can you hear me? No voice now. What of now? Can you hear? Okay, the voice is back, right? Okay, so I will start again. So what I was saying is if you have two springs in parallel, as shown here, now the force F is the force due to this spring plus the force due to this spring. K1 times X plus K2 times X, or K equivalent times X. And our K equivalent is going to be K1 plus. So we can replace that spring with just a single. But we have two springs in series. The force due to this y is moving is going to be K2 in Can you hear me now? You still cannot hear Abdul Hadi? The network was fluctuating. It is back now for me. Is it back for everyone? So it's similar to resistors, but it is just the opposite. If they are in parallel, you just add them. If they are in series, you take K1, K2 over K1 plus K2. The same thing for the damper. If they are in parallel, you add. If they are in series, you do B1, B2 over B1 plus B2. Now consider this mechanical network. Where you have F, x1, the spring constant, the mass, x2, and the damper. Actually, we can replace this with its electrical equivalent. So the force is going to be like your voltage source. The spring constant is going to be like your resistor. And these ones too are impedances. The mass is another impedance, and the damper is also another impedance. Is it okay? So this becomes easier for us to analyze because we are in electrical engineering. Once it is in this way, then halas, it becomes easy. We can now say, okay, this is, you can find the voltage drop and other things, and it's easier to work with it in this way. But we will not go into details of this. Another example is the automobile suspension system. This is an example of, this is just telling you an example of another mechanical system, right? So think about your car. We can model each of the shock absorbers as a spring with a damper in parallel with a damper, another spring in parallel with a damper. So we can actually convert it to one spring, which is this spring in parallel with this spring. Remember, the spring constant is going to be this plus this. And then this damper in parallel with this damper again, the constant is going to be this damping coefficient plus this one. So we can have something like this. This is the mass, this is like the ground, x1 and x0. So this makes it easy to analyze. You see, we started with the car, we looked at the wheels individually, and then we can combine them to form a simple block diagram. Is this okay? Is it clear? Okay. So what are the forces acting? Right? So we have here, this is a mass with displacement 0. So we have the Newton's force, mx0 double dot. We have the force due to the damper, which is b into x naught dot minus x1 dot. And we have the force due to the spring, k into x naught minus x1 is equal to. So we know this equation is easy. The next equation we can write is, we can look at the effect of x naught and that of x1 and equate them. The force due to this one and the force due to this have to be equal. So the force here is going to be, again, due to mass, damper, and spring. So mass, damper, and spring. Now notice the mass is not directly connected to x1. It's only the spring and the damper. So this is the force for the damper and for the spring for x1. You can equate. So these are the two equations we can write. And if you take the Laplace transform of this equation 2, you will have something like this. And then we can easily write our transfer function. Is it okay? Or another way is, okay, I didn't explain it properly. From this equation, you can actually get to this equation directly. You can either write it by looking at this, or once you write this one, you can get to this. So you are just collecting like terms, right? mx0, bx0, kx0. This minus, when it goes to the other side, becomes plus. Same thing, this becomes plus. So once you get this equation, take the Laplace transform, assuming 0 initial conditions, and then our output over the input. So in your car, the input usually is when you get a pothole or a disturbance at the tire. Now this will make the body of the car to move, right? So this is the input, this is the output. That is why we have output over input. Right, so this is it for translational systems. Are we okay, or we want more? We want more, right? We should finish mechanical systems today. And then maybe, let me see. We still have 1 hour, so we can do. We don't have we lecture on Wednesday, National Day. Can you hear me? We will not have lectures on Wednesday. So it's better we just finish this. Don't worry, it's not difficult. We can finish it in 15 minutes, say. And then we know we don't have to be looking for time to do this. If we don't do it now, we may have to look for time to fix and do it. I know it's a lot of material. Just bear with me. We just have 10 more slides. We've covered 20 slides, so what we have left is not much. And the concept is the same, right? Are you okay? Happy to continue? Okay. So, just the way we have the spring, we have what we call the rotational spring, right? You can see some of their pictures here. In the rotational spring, it is the same. The force, in rotation, we don't talk about force. When we go to rotational motion, instead of force, we now talk about torque, T. Now, if you look, the torque is just like Hooke's law, is the constant times angular displacement. Now, since we are in the angle, T1 minus theta1 minus theta2, right? Again, there's the rotational damper. Again, the torque is the same coefficient. Then this one, angular velocity minus angular velocity. And then the moment of inertia, instead of mass times acceleration, it is moment of inertia times angular acceleration. So you see, it's just the same with the translational motion, only that now we have rotation in these things. So we'll see this example. Moment of inertia is like it is like mass, but in the rotational in rotation sense, right? So if you have a rotation body, if you are talking about the mass of a translational system, once it starts rotating, then you have to talk about the moment of inertia. Is it okay? So that's why I told you. Remember, Newton's law is mass times acceleration. Now this becomes moment of inertia times angular acceleration. No, they are all mechanical systems, but in translational systems or linear system, we have mass, and in rotational system, we have inertia. Is it okay? So, as I was saying, so here we have an applied torque, the moment of inertia, the angular acceleration, and then there is a damper here. So the torque is just the torque due to the moment of inertia plus the torque due to the damper. That is it. Just we know that this is J. So when you take Laplace transform, this becomes S omega. So this is capital omega, and this becomes F omega. And then we can collect like terms and then write the transfer function. You see, straightforward. Now, consider a DC motor. A DC motor can be controlled using what we call the field current or the armature current. So this is like the circuit diagram. From the field, we have the field resistance and the inductance here. And this is the armature side. We have the armature resistance, inductance, the current, and then we have a conversion to rotational force here, where you have the inertia and friction, angular velocity, and what do you call it? Angular displacement. So don't worry about this equations. They look too long, but don't worry. So the flux, now when there is a voltage passing through this VF, there will be a flux developed here in this inductor, and that is proportional to the field current. So the flux is the constant times the field current. Now this motor also has a torque, and the torque of that motor is the product of K1, that constant Kf, the field current, and the armature current. Or you can say it is proportional to the armature current, because we know this Kf, If is phi. So we can replace Kf, If with phi, and then we have K1. So we have this equation for the torque of the motor. Now here you just do your normal. The next one, you just do your normal KVL around this loop. So VF is RF times IF plus LF S times IF. So KVL around this loop. Now the torque of this motor loop. Can you hear me now? Is it okay? Okay. You know what? Okay. You know what? It looks like we are tired. So let's leave this this modeling of motor till next time. Next time we do this, and then we continue from there. Is that okay? Okay, thank you very much, everyone. So that means we don't have, well, maybe till next week before we meet again for the lecture. Okay? Okay, thank you, everyone.